Hello everyone, my name is Ravi Balakrishnan. I am a senior solution architect focused on database services here at AWS. I primarily work with our partners, both technology partners as well as consulting partners, with their database modernization efforts. Today, we are here to discuss about application modernization with AWS purpose-built databases. Let's dive in. We'll primarily focus on four major topics. First, we'll try to understand what exactly is a modern application. Then we'll try to dive into some of the reasoning behind why we need a purpose-built database strategy. And then we'll look into the actual databases offerings we have, and followed by how a partner can help and how a typical engagement of adopting purpose-built database strategy for modernization will look like. To begin with, what exactly is a purpose-built database? What exactly is a modern application and why it needs a purpose-built? Let's define a modern application. A modern application has various factors that are unique, like a number of users. User growth is very common and many applications need many users. We are talking about thousands into millions. The data volume has crossed the gigabytes and now it's measured in terabytes and petabytes. They are no longer regional or local applications. They are often global, accessed by various users across continents and time zones. Performance requirements have entered into microsecond latency area. Milliseconds are no longer acceptable for some of the transactions. And developers, from a development standpoint, they would like to scale these applications virtually unlimited so that they don't have to plan about number of users or number of transactions. And they would like to have API-based access to make it easy to automate. And from a payment model point of view, they would like to have it in a pay-as-you-go pricing model so that these applications become more effective from a financial standpoint as well. Some of the examples could be an e-commerce application or a social media kind of application or an employee collaboration kind of application. All these applications have these common factors of users, volume, performance, and payment models. But if you look at the various applications that have been developed and consumed over a period of time, let's take a look at 1970s. We had mainframes. They were monolithic, and in 80s they become more distributed in nature. There was a database layer and application layer, and then in 90s, with the introduction of internet, we had these three-tier applications. Three-tier applications have their own dedicated database layer with web and app layers, but the database layer was still a single layer, most likely a single database from a single vendor. But if you see the progression from 70s to 90s, there has been a lot of advancement in the application layer, but the database layer was still stuck to be a single monolithic entity. And it was become a standard in many organizations such that there will be one master database and all applications will point to it, and this is how it is done and it will be done in the future as well. That's the kind of mindset many developers entered into. Today, it's not the case anymore. Many organizations are considering a microservice-based architecture. It's no longer one application tier. There could be hundreds, if not thousands of microservices connecting to various databases. A single source of truth is required, but it doesn't have to be stuck in a single database instance. There could be more than one. If we try to zoom into the database layer alone between a client-server application and a microservice application, the database was a potentially single point of failure, which is also considered a single source of truth. That is the main positive point many organizations consider to be a single environment. All the applications, all microservices will point to that single database. if there is a new requirement, new application needs to be developed, a DBA has to go in and make sure that it can meet the required performance goals. Soon enough, database became a performance bottleneck. Another aspect about this single database model was each application or each microservice has a different kind of data requirement. One service was focused on a batch application development, or another service was more a lookup nature. There could be a service which is more transaction oriented. There might be a service which was dealing with thousands of rows at a time. There could be a service which only handles one row at a time. And the data model was always different. So tuning the database to meet various use cases was not an easy task. Many database vendors came up with this concept of many features stuffed into a single database to make it work for various use cases. That was a good selling point for them. But the challenge was it was a burden to maintain various components, options, and features, and tuning this was a continuous nightmare for the database administrators. The main solution for such a problem was decoupling this particular database layer into smaller databases. As you can see in this particular slide here, each service can have its own associated data store or a database. That database no longer has to be the same database that we used to have in the past. It could be a different kind of database technology. It could be something that meets the specific need of that particular application or that particular service. This decoupling also gives the agility for the developers to innovate on individual component, not just at application layer level, but also at the database level. They can adopt new features of the database much faster without thinking about breaking some other functionality. It's all self-contained that we can leverage all the features that are required. Picking the right database for individual service is what we call it as a purpose-built database strategy. Here, data needs are different. It could be a massive data volume. It could be a data that is required for high-speed rendering, or it could be a data warehousing use case. It could be a key value lookup use case. We can pick the right database for that right use case. One size fits all is not true anymore. We at Amazon.com took the same approach when we migrated 75 petabytes of internal data stored in approximately more than 7,000 Oracle databases to multiple AWS database services. We have leveraged DynamoDB, Amazon Aurora, Amazon RDS, and Redshift for various use cases. In most of these cases, the migration was done pretty seamlessly and often with minimal downtime. An e-commerce application like Amazon.com cannot afford too much downtime, so we have leveraged some of the techniques to do the migrations in least possible downtime. So when you are developing your own application, or when you are migrating your application, what options do you have on AWS? But before we dive in, let's first categorize the kind of database needs or data models. In the beginning, it was all relational. That's how, when we first thought about database, it was always a table format, a row and a column. And any transactions done on these databases required referential integrity and ACID compliance for all the transactions. There is also a schema that is commonly defined very early in the design process, and changes were not so common to the overall structure of schema. There could be minor changes, but it's pretty much stays the same for pretty long durations. For these kind of relational use cases, we have services like RDS, Amazon Aurora, and Redshift. The next common data model is key value. When we say key value, we are talking about data stores where access is always done on a particular key. It could be high throughput uh, access to items in a particular item table, or looking up orders in an order table. There is always a key, and you are looking for high throughput read and write access to that. And the scale is also pretty immense in this kind of key value kind of data stores. We have DynamoDB for these kinds of use cases. The next kind of data model is DocumentDB. Here, DocumentDB purpose is primarily store documents and quickly access querying on any attribute, not just one key. We also have in-memory database model where the key driver is access in terms of sub-milliseconds. Milliseconds are no longer acceptable here. For this, in-memory databases powered by Elasticache are a pretty common use case here. Then we have graph data use case where we can quickly and easily create and navigate relationships between the data. Here, relationship is the key, like a social network or fraud detection and dependency mapping in networking or asset dependencies. All these things we can analyze in graph databases. Time series data model is becoming more prominent these days, particularly with all IoT data. Here we are talking about a particular attribute change over a period of time. There are thousands and millions of sensors or devices out there. They are sending data and we are storing them in the order that we are receiving. And the analysis is often done on a time scale. Time is the most important scale here, the most important aspect when it comes to analysis of this time series data. For that, we have time series databases. Similarly, Ledger database provides a complete, immutable, and verifiable history of all changes to one particular application data. And finally, we have white column data stores in terms of Amazon key spaces that is compatible for Apache Cassandra. We'll dive into these individual databases in next few slides. But let's try to put these database options in terms of how an application is migrated or built on cloud. As a partner, you might be required to do a migration of particular database. Or as an end user, you are required to migrate a particular application to AWS. So what options do we have? Let's try to put an application lens first. There are two ways to migrate. First, we are doing a lift and shift of the application, or we are building a new functionality or modernizing that existing functionality. Lift and shift is primarily focused when we are having a requirement to quickly do the migration. It could be a timeline that we need to meet, or a specific event that we have to meet, or you don't have enough bandwidth to make a lot of changes. You want to quickly do the migration. In that kind of migration scenario, Amazon RDS is the first choice. Most likely, your on-premise application would be running against a relational database. Amazon RDS is a managed relational database engine. We have multiple database engine options available here. From a commercial standpoint of view, you can run both Oracle and Microsoft SQL Server. We have MySQL, PostgreSQL, and MariaDB as open source database engine options. We also have Amazon Aurora, which is a purpose-built, a cloud-native database, if you will. But in all Amazon RDS engines, there are four common benefits or four common themes of advantages that as a customer or end user you will get. First, they are easy to administer. You're not talking about installing and racking and stacking your hardware. There is no need to think about operating system installations, patching and hardening the operating systems, and even the database software installations and patching. All these are taken care by AWS for you. We also take care of availability and durability of these RDS environments. For all RDS engines, you should be able to quickly provide high availability using multi-AZ option in a matter of one single checkbox, and your database is automatically highly available across two availability zones within a region. Even important activities like backups and restores are also automated, and you can access them as a matter of single API. Scalability is another important aspect when it comes to database migrations, and even migrating on-prem workloads to AWS. Scalability is often not paid too much attention. In an on-prem environment, you provision a database with certain capacity and you're basically stuck with that. And you have to plan and provision for the peak usage. On RDS, you don't have to run your infrastructure for peak usage all the time. You can scale the database when there is a need, both compute as well as for the storage layers. And most importantly, these are fast and secure. All RDS engines are optimized with best practices for performance, and we have multiple options for security in terms of encryption in both transit and at rest. Amazon Aurora, you can think of it as the next step to Amazon RDS. Amazon Aurora is MySQL and PostgreSQL compatible relational database built for the cloud. This Aurora can provide enterprise-grade database performance at open source database cost. Essentially, you can get performance and scalability features that are typically available in commercial databases. And if you compare with a standalone self-managed MySQL environment, you can get 5 times more throughput on Aurora MySQL. If it is a PostgreSQL environment, you can get 3 times performance of a self-managed PostgreSQL. You can easily scale these workloads with up to 15 read replicas. From availability and durability point of view, Amazon Aurora is deployed across 3 availability zones in a single region, and we automatically maintain 6 copies of your data across 3 availability zones. This provides much higher availability and a fault tolerance. Backups are automatically taken to Amazon S3 as well. As always, Amazon Aurora is highly secure with options for both encryption in transit and encryption at rest, and this is fully managed. To simplify the migration of your database to AWS DMS, we provide simplify the migration process, we provide AWS DMS service. DMS is a database migration service to migrate your on-premise databases to cloud databases, or even vice versa. You can use it for one-time migration use case or continuous replication use case. More than 100,000 databases have been successfully migrated using AWS DMS service. DMS essentially helps you to do the migration from both same engines like Oracle to Oracle, or heterogeneous migrations as well, like Oracle to PostgreSQL if you're trying to modernize. DMS primarily focuses on database migration, and we also provide a tool called schema conversion tool for conversion of the schema objects like PL/SQL procedures and functions and index definitions, etc. So between Aurora and RDS, what kind of applications are right fit, or where you should definitely consider RDS based offerings for your database layer? If your database is self-managed in an on-prem environment or even on Amazon EC2, or for that matter any cloud, if it is self-managed, migrating to RDS will give immediate value. Your DBS need not spend time maintaining and managing those environments. They can spend more time focusing on your business needs and help your application developers and optimize your application functionality. And you should also consider RDS if you are not planning to re-architect the entire application and you want to keep majority of the application as is and you want to migrate with minimal changes, then RDS is a good option. This is often simplest way to get started. Let's look at the use case where you are deploying a brand new application or extending an existing application functionality. In these cases, we often recommend you that you start with the data model. It could be relational, key-value, or graph, or could be any other data model. Let's dive into some common data models. Most of you might be familiar with a relational database model. This is structured in tables. There is certain relationship between the tables, and often data consistency and accuracy is required, and transactions have to be asset compliance. This is a common use case, and you can address these requirements with Aurora. The next kind of data model that is quite common is key value. The key value data model is where you have data organized in a key and value pairs. Like as we are showing in this particular slide, we have a gamer tag and various attributes associated with those particular gamers. Most of the data is accessed as per that particular gamer tag. You're putting the data or getting it by the tag. For these kinds of use cases, we have Amazon DynamoDB. Amazon DynamoDB provides performance at scale. Here we can get consistent single-digit multi-second response times at scale. We are talking about even millions of transactions and guaranteeing that kind of latencies for your operations. This is a serverless architecture. This is quite important because we are talking about performance at scale, and if you are dependent on certain infrastructure capacity, making sure that you get consistent performance means that you often have to over provision in a traditional environment. In DynamoDB, as it is serverless, you don't have to think about any capacity. In fact, you can even leverage DynamoDB auto-scaling capability so that you don't have to think about how much of read and write capacity you need. The service will take care of scaling by itself. As always, this is secure. DynamoDB provides both encryption at rest and transit. And the unique feature is it also provides you global replication capability. You can make sure that data is available across multiple regions for your applications that are global. The other data model we are talking about here is graph. Here, relationships are the first-class objects. What exactly we mean by that? Here we have vertices and edges, essentially a data object as well as its relationship with other data object. And if your application needs to query these relationships, like person A bought a product X and what else he could buy, or he follows certain theme, what else he could buy, a certain recommendation, or traversing a relationship in general, a graph data model is the best place to start. Amazon Neptune is a fast, reliable graph database engine built for the cloud. It is open, fast, reliable, and easy. Essentially, if you have any application, a graph application developed using Tinkerpop or RDF data models and leveraging Gremlin or SparkQL, you can directly point that particular database to Amazon Neptune. Amazon Neptune is also powered by similar kind of storage engine like Amazon Aurora, providing 6 replicas across 3 availability zones with full backup and restore capabilities. Amazon DocumentDB is another database mainly meant for document-based data model. If you have an existing application that is running against MongoDB, you can use the same code and drivers that you use with MongoDB, point it to DocumentDB, and you can easily do that migration. MongoDB provides millions of requests per second with millisecond latency, and it provides 2x throughput compared to a managed MongoDB service. And it is a fully managed RDS engine powered by similar availability and durability characteristics like Aurora. Amazon Elastic Cache is answer for all those in-memory data store requirements. Earlier we discussed about a consistent sub-millisecond response times or session store kind of requirements for in-memory databases. Amazon Elastic Cache has both options for Redis and Memcached, providing consistent high performance for those in-memory requirements. Here, the key is sub-millisecond response times with unlimited scale as a fully managed database service. Other service is Timestream. We discussed this about Timestream kind of data generating from devices where time is a key factor of a measurement. Amazon Timestreams is that fully scalable and fully managed time series database. This is 1,000 times faster and one-tenth of cost compared to relational databases for time series workloads. If you're trying to store time series data in a relational database, technically you could do it, but it would be a nightmare to maintain and manage all the time series data over millions of devices. Amazon Timesheet makes all this management easy. The most important aspect is this is serverless, which means that you can easily scale from few devices to millions of metrics pretty easily and without having to think about hardware provisioning and planning and all the maintenance activities. Amazon Timestream provides all those capabilities for you. QLDB is another database that we mentioned earlier, is a fully managed ledger database. I want to highlight the kind of use case you have here. Think of like a HR information database, and the application requirement is that you want to maintain history of each and every change, who changed what, and you want to keep it for historical research purposes or validation purpose. You can do it in relational DB by maintaining audit tables, triggers, and all other constructs. You can do it. In fact, many customers do that today in a relational database, but it becomes a tough to manage because over a period of time, your audit data becomes bigger than actual data. That is not efficient to manage. QLDB provides that immutable and transparent way you can store this historical track history essentially, and you can store it in a cryptographically verifiable way. Essentially what it means is that you can make sure that all changes are cryptographically chained and verifiable to give the guarantee that it was not modified or touched or not tampered in any way. This QLDB is highly scalable and executes 2 to 3 times as many transactions as ledgers in a common blockchain kind of frameworks. Another database is Amazon Keyspaces. Again, this is primarily focused on those applications built on Apache Cassandra. Amazon Keyspaces is a managed database for those Cassandra compatible workloads. This is highly available and secure. And the most important aspect is this is a serverless service, which means that you don't have to think about servers to manage and build clustering and all to migrate those workloads. How do we put all these databases together? We'll just run through a sample use case of how one customer has done it. As we all know, the data is growing rapidly. DevOps means developers are making changes more rapidly, means more data is coming into the databases and more variety of data is coming into the databases. Let's see how one customer has solved it. This customer had a Microsoft SQL Server deployment on-prem and lots of hundreds of databases deployed across multiple instances. These databases were used for various use cases like session store, logging, transactions, and batch. As a first step, this customer migrated all these SQL Server databases to RDS SQL Server and SQL Server on EC2. We provide a tool called Schema Conversion Tool to analyze these workloads, analyze on-prem SQL Server databases to identify which database is right fit for database and which database is better suited on a SQL Server EC2. Once the initial migration is done, they started with the modernization journey. They started with those easy workloads like a logging, which can be migrated to Elasticsearch service, or a key value lookup information that can be migrated to DynamoDB, something like session store, or rest of the database migrated off to Amazon RDS and Aurora. In this model, they were able to reduce the dependency on a single vendor, single Microsoft SQL Server environments, and they were able to pick right database for right target. As you can see, this whole database management system market is exploding. By 2022, 75% of all databases will be migrated to cloud. As a customer, you have the opportunity right now, or as a partner, you have the opportunity to help all those customers to break free from those databases and migrate to AWS managed database services. Many customers have already done it. They have seen the success of leveraging these purpose-built managed databases, and you can get started too. We recommend that you first take a look at APN Navigate program, where you can have a self-paced online training on all database services that we have mentioned, and then you can request AWS team for deep dive workshops. The easiest way to get started is start with learning. We have some links available here on various resources. Join the APN partner programs and engage us for all the deep dive conversations. Hope this session was useful for you. Thank you very much. Please do fill in the session survey below. Thank you.